So something to know about what we're going to do with relations, there is a number of things that we're going to be doing with relations that are not in your textbook. He does a very minimalistic viewpoint. We're going to push it out and do a little bit more with it because this is our background, or okay, it's not a background topic, but it is the topic that we really need to have a strong foundation in to deal with one of our future topics. Okay. But in terms of where they're in section 14 and 15, and today we'll just be in section 14 of your textbook. Because 15 deals with what's something called equivalence relations, which I don't think we're going to get to today. We'll realistically get to that tomorrow and then on Friday. So the first thing is, what's the definition of a relation? At this point in your mathematical career, you guys have what? You have progressed at least through high school. You've probably taken at least one college course, maybe not, but even if you only had a freshman math class in high school, you have dealt with relations before, even if you don't remember the name or if your teacher didn't tell you the name. So here's what a relation is. First of all, the relation is defined between two sets from a set A to a set B. That order does actually matter. In terms of notation, this is more function notation, but all functions are relations. One of the things you'll often see is something like this. Well, this is actually function notation. But what it tells you is you started in A and you ended in B. And that arrow gives you the direction of where you start and where you end. In terms of functions, domain and range, A would be the domain, B would be the range. Okay. Now, let's actually look what specifically a relation is. A relation, R from a set A to a set B, is simply a subset of A cross B. And remember what A cross B was. This is defined as all of the little ordered pairs, A and B, where little a comes from set A and little b comes from set B. Notice here this order matters because remember when we talked about cross products, what happens if you reverse this order of the ordered pair? It's a different ordered pair. Okay? So this A and B, when it says from set A, that's telling you the first position, to set B, that's telling you the second position. Okay. Now, this next thing isn't really part of the definition, but it's something that you will typically see in terms of how you select which of the ordered pairs from your cross set to use in your relation. There's either you'll just be told what the ordered pairs are explicitly, so they'll be listed out, or your relation would be defined in some sort of verbal description or mathematical description. And I'll show you the three main different ways that you can see relations described. Okay. Now, you can also be told, hey, you got some relation R, and all you're told is on set A. Notice if you're missing that second set, this actually means that your relation is some subset. Remember the simple subset here is some subset of A cross A. Notice what this means. This means that your second set B actually equal to A. Okay. So if you're only given one set, you use it for both parts. Now, the last little definition we'll have before we get into the several different examples to see how relations can be defined or described or given to you, if you will, is this thing. And this is now dealing with the elements. So this says little element A is related to little element B by the relation R. Now, what does that mean? This tells you that if R is some subset of A cross B, in other words, it's a relation from A to B, then A is related to B means you actually have the ordered pair little a, comma, little b inside of your relation. And by shorthand, we typically write it as A related to B, not with the ordered pairs. 100% correct to write it with the ordered pairs. Writing it with the ordered pairs definitely pulls us back to the subset or the set notation, but when you get up into relations, people have a tendency to be extra lazy. And notice here, what do we have? We have 3 symbols to write as opposed to 1, 2, 3, 4, 5, 6, 7 symbols to write. Okay, so this is the lazy way of writing that. And it doesn't matter which way you see, you'll see them both. Okay, so those are the definitions. Now we'll have some examples. So the first example, notice what it tells you. It tells you right here that, hey, your set A is a set of all integers. Your set B is also the set of all integers, and the specific relation that we have right here is comprised of these ordered pairs, 1, 2, 3, 3, 4, 4. And notice since both A and B are the set of all integers, all of our elements in our ordered pairs, all of the positions in our ordered pairs are all integers. This guy right here is what is known as a finite relation. Any guesses why I would say it was a finite relation? Don't overthink it. The buzzword there is finite. Anybody have a guess? Finite relation? So suppose you had a question and it says, do this, 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 whatever it says to do, with a finite relation. If it wants you to find some finite relation, what's the key thing you'd have to do to make sure your relation was finite? Any guesses? So in terms of finite, all finite means is you can literally count them up, and at some point you stop. Okay? So there's an end. It doesn't keep going on and on forever. In other words, if you're dealing with cardinality, and remember our relations here are just sets of ordered pairs, what this means is you actually have a cardinality. You will have an integer answer for your cardinality. In this case, there's exactly 3 elements or 3 relationships inside of your relation. That 3 means you're a finite relation. Now, on the flip side, if you have an infinite relation, what does that mean? That means you have infinitely many ordered pairs and they keep on going forever. You couldn't actually write them all out. You'd have to, if you started to write them out in pairs like this, at some point just put dot, dot, dot. It keeps going. I can't keep writing them out. Okay. We are going to be looking in this class mainly at finite relations. However, in something like an algebra or a calculus class, they often, more frequently, are going to be looking at infinite relations, okay? Just to sort of throw that out there to tie this in with other classes, okay? So this is one way to see the examples. You explicitly have all the ordered pairs written out. Quite frankly, you'll see this a lot in our class. I'll literally give you what those guys are, okay? Now, this second way is also extraordinarily common way of seeing your relation written out. And notice here, it's a little bit more subtle in terms of what the relation is. First one is, we define only one set, not both an A and a B, although to be fair, in this particular case, your A and the B did happen to be the same set. For the second example, we only define a set A. If you're only given one original building set, that does mean you use that set for both parts of your cross product. So this says 2 elements of your set A are related to each other, and here we named the relation capital R. If the name of your relation is some other letter, you put whatever the name of the relation is right there. So let me actually write that in. So this R, so we're looking at relation R. Okay? Now, this if and only if, this abbreviation for if and only if, tells you exactly what the criteria is in order for those elements A and B to be related to each other. This tells you that A has got to be smaller than B. Now, let's actually write this guy out. So, if we wanted to write out our relation, what would be an ordered pair that's in that relation? Now, I'm going to go ahead and throw this to you guys. What do you guys think? What is an ordered pair that's inside of this relation? I'll preface us with having the right symbols. You guys tell me what numbers to put in here. There's going to be at least 2 ordered pairs. Yep, that would totally be one that would work. So 1, 2. How do we know? Because 1 is smaller than 2. And 1, 3, that would also totally work. 1 is smaller than 3. And now the question is, once you have those guys, is there any other ordered pair that starts with 1? What do you think? Is there any other possibility that we could have where the first position starts with 1? This is thrown out to you guys. What do you think? Could we start with 1 and have some other number at the second one? Correct. You can't, because the only other option that you have up here is 1 and 1, 1. Well, 1 is not smaller than itself. So you guys are totally right there, which means we could maybe start with a 2. What do you guys think? Is there any ordered pair that starts with a 2? Hint, it's not 2, 1. Yep, 2, 3 would work. So 2, 3, 2 is smaller than 3. 3 is actually the only number bigger than 2 in this set of 1, 2, 3. That's literally it. That's all we got for an ordered pair that starts with 2. Now, last question is, do we have any other ordered pairs? Well, the only other possibilities is if we start our ordered pairs with a 3, based off of our criteria, could we start an ordered pair with a 3? Is that possible? What do you guys think? Yeah, it also turns out you cannot start with a 3. Why? Because 3 is the biggest number, so there's no number bigger than 3 in this set. So for this guy here, it was probably almost easier just to write out those ordered pairs. Now, if our building set A had been much larger than 1, 2, 3, maybe it was all integers like before. If you had all integers and had this inequality, well, you would have all of those same ordered pairs, but you would also have tons and tons more. In fact, you would have an infinite relation or infinitely many ordered pairs that you'd be dealing with. Okay? So depending how big your relation is, all depends on this building set here. It also depends on what the actual ordered pairs are as well, but it's definitely closely related to this guy right here. Okay? Questions make sense? Kind of feeling okay so far? Because the next question I truly am going to throw to you guys. It's going to be one of those poll everywhere questions. So any questions before we move on to the next guy? All right, I'm not seeing any. So this next question is totally for you guys. I see that a couple of you guys have already started putting a guess. Notice I did not try to make this a complicated question whatsoever. This is written in the format or the third format that you can see for a relation. So while you're taking a guess of whether you think it is a relation or not, this is a set builder notation. You've got the building set that we have is right here. A equals all real numbers. And the part that I forgot out of the set builder notation right here is this guy, the set A, the little x's and y's, both of them are going to come from our set A. So they're both going to be real numbers. So this says we have a bunch of ordered pairs. The condition attached to these ordered pairs or attached to the real numbers to put them into the ordered pair which we care about is x squared plus y squared equals 16. And what we want to know is, while that's totally something that you can have to build a set with, is that set itself also a relation? And that is the key question. And I see most of you have a guess. The last one now of you want to make a guess as well? Because I don't want to show you the answer if you're still guessing. All right, so let us see what the correct answer is. And what I'm going to do is I'm actually going to first see what you guys said. Oh, awesome. It is split. Luckily, it's not 50-50. All right, so it turns out, how do you tell if somebody is a relation? A relation is literally just looking at, is there some sort of relationship between your two ordered pairs? So your two elements of your ordered pairs. So in this particular guy, went ahead and prepped up the exact same situation right here, or almost. It's written out a little bit differently here. It's not written out in that same set builder notation. So this means the exact same thing. This says, hey, we've got some building set. Our building set is all real numbers. We're going to define a relation. X is related to y by the relation R, exactly when x squared plus y squared equals 16. Now, that right there tells you we are building a relation. So this tells you in this notation, you definitely have a relation. If we go back to our other bit right over here, how would you know it's a relation when it's written in this set builder notation? The key giveaway is, I don't know if I can write on this. Nope, it's not letting me write on it. The key thing is this part right here. If you see this ordered pair of x comma y, and everything is coming from the two sets right here, you've got a relation. A relation is the most general object that you've got, where you are, here's why it's named a relation, two objects related to each other in the format of an ordered pair. Okay? So if you've got some collection of ordered pairs, you probably have a relation. Now, this guy here, if we want to see what this relation is, and there are two questions. One of the questions that we're going to look at is this relation an infinite or a finite relation? And the second thing we're going to look at is what does this relation represent? So this one is the closest to looking like something you would have seen in an algebra or a calculus class. Anybody notice what that relationship right there looks similar to? Not something we've talked about in this class, but something you would have talked about in like an algebra or a calculus class. In other words, does it look familiar? If so, what of? Or what to? Ooh, that is not right grammatically. What does it look like? There we go. So what do you guys think? Is it familiar? If so, what does it look like? That's this formula. This is true. It does look exactly like the formula of an a squared plus b squared equals c squared. Not what I was shooting for in terms of looking for an answer here more algebraically, but yes, you are totally right. This is actually looking at, I'm assuming you're referring to Pythagorean's theorem there in terms of what you're thinking about. And yeah, that's actually how or why, or how is probably better, how that formula was originally developed. And I'm sort of lying to you, but not really, how that formula was originally developed. I was thinking more in terms of shapes. So if you try to graph this thing, and why would I refer to graphing? Because our two sets are the real numbers. So if your two sets are the real numbers, you can graph things. You're correct, this guy is totally a circle, center at the origin, and a radius of 4. Please note my horrible, horrible looking circle. Okay? Now, I'm assuming that all of you guys have dealt with graphing circles before. I'm crossing my fingers. Hopefully that is an accurate representation. So what happens here, what do you know? This guy is not a function is one of the things you would have been told in those previous classes, but it is still a relation. Why? Because there's some sort of relationship between your x's and your y's, your x coordinates and your y coordinates. Now, that being said, this is an example of an infinite relation. If we actually tried to write out all of the ordered pairs, well, some of them would be easy, but there would be infinitely many. We could not write them all out, which is why we have our set builder notation that we saw on the previous slide, or this formula. Okay? And that's also why people like picture representations. Why? Because you're dealing with infinite relations typically when you start graphing things. Okay? So those are the three main types of relations that we'll see. The ones where you explicitly have the ordered pairs given to you, the ones where there's some sort of formula, like what we had right here, or the inequality formula, or the ones with set builder notations. You could see any of them, but the first one's the most common for us. And I believe today I've done all of our next examples where I just give you all the ordered pairs. Okay. Now, the next definition before we get into some mechanics of how we I can't speak today, how we make pictures visibly represent our relations. One last definition before we get into that, and this is something called the R relation set of some element X. So here's the background. You have some relation R. It's on the set A to the set B, or from A to B. In other words, your relation is a subset of the cross product A cross B, and this X is somebody in the domain-ish. Okay. Technically speaking, your domain is only the x's in the first coordinate that you use, and the range is only the elements in the second coordinate that you use. And I can write that over to the side. I don't think I have. So let me throw in this here, and then we'll put that notation over to the side. So then this R relation of your element x, or if you prefer, put an A in here, is all of the little b's from the second coordinate where x was the first coordinate. So if we put in an example here, suppose your relation is something really tiny. So maybe 1, 2, maybe 1, 3, maybe 2, 3. In other words, In other words, this same guy that we had previously. Okay, so that was the same one, our second example that we had a while back. In this case, if we looked at this R relation, R actually for range, and it has another symbol I'll show you in just a second. Any guesses what elements would be in this R relation of the element 1? Don't overthink it. Anybody got a guess? What elements from set A would go in these squiggly braces right here? Your only options are 1, 2, or 3. Maybe none of them, maybe one of them, maybe two of them, maybe all three of them. What do you guys think? So in terms of this capital R, which is a really terrible notation actually, if you have this capital R of 1, this says these are all the second positions of your ordered pairs that start with 1. So if you prefer, let me close the curly braces over here. Close the curly braces over here. This is, in terms of set builder notation, all of the elements from A such that 1 comma A. And we'll do the same thing down here for the element 2. This would be all of the elements in your building set where you're looking for 2 comma A. So with that information, what do you think? What's the missing number? Because I'm going to claim there is a missing number that should go right here in that R relation set of 1. Yep, so that would be 3. And notice, how did we get this? We looked at the 2 ordered pairs that started with a 1. Now, using that exact same logic, what should we fill into the R relation set of 2, the one right below? That should also be 3, and it will only be 3 because here we looked at that ordered pair 2, 3, and there was 1 ordered pair that started with a 2, so you only had 1 element. Notice if you actually pull or merge, I shouldn't say merge, if you count up all of the elements in all of your R relation sets, you'll get exactly the same number of individual elements as what? As number of ordered pairs, and they'll actually just be pulled the last guys of all the ordered pairs. Now this R relation set is also called something else. The higher up in math you go, this is also called the image of X. And in terms of symbols, it looks like that. Okay. And that is also something that you see quite frequently, but not normally at this level of a class. Now, in terms of domain and range, for a relation, the domain would be all the first coordinates, coordinates used. So in our particular example, right here, our domain would be what in our example? Don't overthink it. If you look through all 3 of those ordered pairs, what are all the first coordinates? What are all the first positions? Here, I'll highlight the relation so it's easier to see. We're looking at this guy. So if we look at our relation right there, what would be the domain of that relation? Because it's actually not the set A. And that's why I wanted to point this out. I mean, you often think of it as a set A, but it's actually a subset of A. Proper or not, it can be the whole thing. So what do you guys think? What would be the domain of this relation R? Okay, so your domain, this is all of the first coordinates. Your range, this is all the second coordinates, and specifically it's the ones that are actually used in your ordered pairs. That's the key takeaway here. All right, so let us now, unless you guys have questions, let us now move on to more of a, how do we reinterpret our relations into a more visual or easier to manipulate, easier to use way. Okay? One of the things that we are trying to get towards is actually looking at properties of relations, and it turns out you can find your properties of relations from the ordered pair format, but you can also find it, at least with finite relations, easier if you do one of these visual representations. Okay? So there's two visual representations that we're going to be doing. These things do actually work with infinite relations, but it gets snarly really, really quickly. So we're only going to focus on these visual representations of relations when we have finite relations. So the first thing that we have is the matrix of a relation. And this is where I forgot to check before class today. Have you guys had linear algebra? Or I should rephrase, you don't have to have had linear algebra. Have you guys played with matrices before? Awesome. So we're not going to do anything stressful with matrices. One of the things I put in this section, in case you haven't played with matrices before, because linear algebra is not a prereq for this course, is I put a, it's probably now 2-3 years ago, I typed up a snapshot of only the matrix manipulations that we would need for our course. Okay? I went ahead and put that little PDF file in our topic section under relations. That way, if you haven't played with relations in the past, although it looks like about half of you have said that you have, you'll be able to have a reference, okay? I will let you know all of the details that you need on how to deal with matrices as we go through, but if I brush through something real quick and you haven't seen that before with a matrix, stop me and we'll totally go over it, okay? The first thing is matrix of a relation, and this is specifically dealing with some relations. So we start off and we have our building sets A and B, and we're going to go ahead and assume that they are finite sets. Notice here with our finite sets, with a subscript, I actually told you here how many elements were in each of those two sets. One of them has n elements, and the other one has m elements. Okay. Now, the relation R is going to be some relation from A to B. So in terms of your ordered pairs of your relation for a relation R, all of the coordinates from the first position are going to come here from, I can't find my cursor, are going to come from set A, and all of the coordinates in the second position are going to come from set B. Okay. Then what we can do is we can actually throw this relation into a matrix, and I'm not being fancy here. This matrix is just called M for matrix, and the subscript R there represents which relation you're dealing with. Now, this is actually standard matrix notation now. The little m right there indicates specifically a position in the matrix. Now, here's the key thing about a matrix. A matrix is just a rectangular shape of numbers, and we're going to see that in just a second. The first coordinate down here represents the row, so this would be the ith row. And the second position here represents the column, so that J would be the jth column. Okay. Now, notice the only two numbers that could be in any position of this matrix. It can either have a 1 or a 0. So this is what's known as a Boolean matrix. A Boolean matrix only has its entries as 1 and 0. Now, let's face it, you guys should recognize that buzzword of Boolean. What is it often used for? It's often used as a check. Did something exist? Did something not exist? What is this doing? You put a 1 if this ordered pair is in the relation. You put a 0 if this ordered pair is not in the relation. So this is literally like building a matrix of a bunch of true falses. Yes, true, it's in the relation. False, no, it's not in the relation. And that's it. That's literally all it is. Okay? So let us look at an actual example. So this example I on purpose have here. I can't find my cursor again. There it is. Set A is 1, 2, 3, the digits or the numbers, and set B is A, B, C letters. And I on purpose made these guys two different types of characters just so it's really easy to tell who's in that first position and who's in that second position. We definitely have a typo there, don't we? So in this particular situation, it looks like I need to, and I'll do the easiest fix. I'm going to add D to set B. Hopefully you notice why I did that, or maybe not. There's a D down here. Okay. So if we want to go ahead and build this matrix, So in terms of building the matrix representation of this relation, here's what you do. First of all, I'm going to go ahead and title it. The second thing I'm going to do is I'm going to put the outer brackets of a matrix around here. In terms of the correct and proper way of writing a matrix, it has to have some sort of things around the outside. The word things is not being very precise at all. You either have square brackets or you have parentheses. You will probably see places where people get super duper sloppy, and this happens a lot in older textbooks where the formatting, the typesetting for math or other symbols was very difficult to do. And one of the things that they would do is they would leave off these brackets and they would just put the numbers in as a rectangular block. Okay? But properly to show where your matrix starts and stops, you need either square brackets or parentheses. I do square brackets because they're easier for me to do on the fly here. Okay? Now, we go back to see how these things were working. Notice here, the rows are indicated with the subscript I, or the index I, and they're corresponding to the first position right here, which means I'm going to go ahead and title our rows, and I'm going to go ahead and title our rows by our first position, which are our A elements. So we have 3 of them. We have 1, 2, and 3. Okay, so the first row is going to correspond to all possibilities where you have an ordered pair that starts at 1. Second row, all possibilities where the ordered pair starts with a 2. Third row, all possibilities where the ordered pair starts with a 3. Okay. And then we'll do the same thing and figure out the columns. The columns, so J represents column. The J here represents our second position, or our building set B, in this case, our letters. So this here would be A, B, C, and D. Now, technically, some of you may have noticed this, technically those two building sets A and B are both sets. What do we know about sets? The order in which you write the numbers or elements of the sets doesn't matter. You can flip-flop, rearrange them back and forth, and that is perfectly fine. In that particular situation, well, the rows or the columns could potentially be scrambled. And the answer is yes, that's true. So what we do is, just like when we were doing using our characteristic function previously when we encoded sets as a string of binary numbers or a binary string, what we do is by default, I can't find my cursor again, there it is. By default, we go ahead and let set A, whatever it was originally given to us, like a 1 through 3, that's the order we deal with rows, and whatever we were given for set B, that's the way we deal with it with the columns. Okay? By default, I'll give these things to you guys in either numerical, so increasing order, or alphabetical order, and if you weren't explicitly given these two and you were going to grab them, just make sure you label them here if you don't do it in the standard increasing order or alphabetical order. Now, that was a ton of aside. Let's actually get in and figure out what this matrix actually is. So this first position right here would correspond to, if you have an ordered pair of 1A. So if we look in our relation, do we have the ordered pair 1A? So what do you guys think? I'm totally going to throw the first couple of these out to you, and then we'll do a few more at a time. So what do you guys think? We're going to go across the first row first. So do we have the ordered pair 1A in our relation? Yep, it's the very first one. So I'm going to go ahead and put a 1 right there. Why are you jumping on me? All right, now, second position, first row, right here. This would correspond to the ordered pair 1b. What do you guys think? Do we have a 1b in this relation? Hint, there's only 2 possibilities, yes or no. You got a 50-50 shot of guessing it right. So this one here, that would be a no. There is no visible 1b ordered pair up in that relation, so we'll put a 0 for no. Now, next one over is 1c. What do you guys think? Do we have a 1c in this relation? Correct. Also a no, so we'll put another 0 for no. And last position in the first row, it corresponds to the ordered pair 1 and then D. So what do you think? Should we put a 1 or a 0 in this last position? Notice I asked the question differently this time. We have the ordered pair 1D, so we'll go ahead and put a 1 right here. Now, I'm going to throw the second row to you guys. What do you guys think the second row should be? In terms of 1s and 0s, you should have a grand total of 4 1s and 0s. Let's see. The guess coming in is 0, 1, 1, 0. 0 to A, nope, that it would be correct. 2B, yep, we got it. 2C, yep, we got it. And 2D, nope, we don't have it, so perfect. Always good when there's multiple people getting the same answer. So, third and last row, what do you guys think? What should be the 1 and 0 combinations for those last 4 entries? All right, I got a couple of guesses coming in, and the guess coming in was a 1, 0, 1, 0, and yes, that is accurate. We do have 3A, we don't have 3B, we do have 3C, and we don't have 3D, and that is literally all you do to build the matrix that corresponds to your relation. That's it. Now, notice an interesting thing about all of the positions in the matrix, including the zeros. If you have 1s on all of these positions, including where we currently have 0s, you would actually have the full cross product of A cross B. So, what does this matrix, this Boolean matrix represent? It's those 1s are literally telling you which elements of the cross product you grab, and the 0s are literally telling you which elements of the cross product you didn't grab. Okay? So there's multiple ways to interpret that. But that's it in terms of relation, in terms of building this matrix. The only thing that people have a tendency to get swapped sometimes is sometimes they'll reverse who goes in the row and who goes in the column. So what I have found is the easiest thing to do is actually write it where you have the labels on the outside. All of the labels for your first coordinates or your first positions, write it here. All of your labels for your second coordinates or your second positions, write it down here. And notice then when you're reading this left to right, like you would read your ordered pair, it'll be that same exact order. Sometimes people try to put the labels over here, and then you have to read everything backwards, and then they'll accidentally twist up the matrix too. And for those of you who know the buzzword, they give the transpose of the matrix as opposed to the actual matrix. All right, so that deals with everything in terms of building the matrix. When we get to properties of relations, we'll come back to the matrix, and we'll get to that either at the end later on today, or we'll get to that at the very beginning of next time, because next time we're going to look mainly at properties. So the second way to visualize or rewrite the information given to you in a relation is by drawing a picture. Technically, what we're going to be drawing is a directed multigraph. I'm going to go ahead and just call it a digraph, which is just a directed graph, just because it's easier and not the whole mouthful. Okay. So if we want to make this directed multigraph or this digraph of a relation, first thing you've got is you have, okay, technically you could do this with an infinite set, but we're only going to do it with a finite set. So you start off with some finite sets, and your relation is a relation on A. Notice here what this means. This means your relation R has to be a subset of A cross A. So unlike our previous example where we had 2 different sets for our building sets A and B, here you have to use the same set both for where your domain and your range you're pulling from. Your domain and your range don't have to be the same set, but they have to be subsets of the same set. Okay? And the reason is how this thing is going to get built. Okay? So in terms of what happens, we're going to build this graph. The vertices of the graph are going to be all of the elements of A. Vertices are going to look like points, and you'll see this as soon as we jump into an example, which will be here in just a second. And the edges of, so actually I can just draw a picture. So something like that would be your vertex. Edges of this graph are going to be directed edges, and specifically notice this condition. This says if we have two elements inside of our relation, this means that in the graph you're going to have the directed edge starting at the first position and going to the second position. Okay? Now, that's it. That's literally all the directions you need. So, let us look at an example. So this example has exactly one building set. It's just the integers 1 through 4, and then it's got a bunch of ordered pairs. So here we've got the ordered pairs 1, 1, 1, 3, 1, 4, 2, 1, 2, 4, 3, 1, 3, 2, and 4, 2. So, what to do? Put the vertices in first. So you look at your building set, which you may or may not be given. If you're given your building set, put all 4 vertices in like what we have. So we've got 1, we've got 2, we've got 3, and we've got 4. Okay? There's different conventions in terms of building graphs. Some people do what I do, which is put the name of your vertex, the number that came from element A, inside the circle. For this particular representation, this specific type of graph, that's probably one of the easier ways to do it. People also just draw a little dot, a little point, and put the label next to it. But in terms of how many arrows we're going to get with our directed multigraphs or digraphs, this is going to make your picture the cleanest to read. Okay. Second thing you do is put in the edges. Note, you can't put in the edges until you have your vertices. I'm going to skip 1, 1 because it's special. So if we start off here with 1, 3, this tells you you're going to have an edge. It's going to start at 1 and it's going to end at 3. So this guy would look exactly like this. Where's 3? Over there. Okay. And notice here I put the arrow on it to indicate that we started at 3 and we ended at 1. So 3 is like the tail. Not 3. 1 is like the tail and 3 is like the head, if you think of it in terms of arrows. Now the next one is 1, 4. So 1, 4 starts at 1 and it ends at 4. The other way that people draw in the direction on edges is they'll put the arrow right in the middle. I'm not going to lie, when I do it, I find it easier to draw the arrow all in one sweep and have it a proper arrowhead, but you can do it either way. It's perfectly fine. The higher up you go with dealing with graphs, the more you need the arrowhead more towards the beginning is more useful, just because the more arrows you have, sometimes it's easier to spot them there. But at the level that we are for this course, every single one of them, you can always have the arrow down here at one end. Okay. So that takes care of 1, 3 and 1, 4. Next we have 2, 1. So you start at 2, you end at 1. Now note something about reading these ordered pairs. I'm going to start reading and drawing at the exact same time, and notice what happens. The next ordered pair is 2 to 4. Notice when I drew it, it was 2, 2, 4. Next ordered pair is 1, 3. So it's 3, 2, 1. The next ordered pair is 3, 2. So that's 3, 2, 2. The last ordered pair is 4, 2. So that's 4 to 2. Notice some of the pairs of vertices that have edges between them. Some of them have exactly one edge, like 2 and 3. Some of them have 2 edges, like 2 and 4 right here, and that's totally fine. You have 3 possibilities. One possibility is no edge between your pair of vertices, like 3 and 4. Exactly 1 edge between your pair of vertices, like 2 and 3, or exactly 2 pairs of vertices, not 2 pairs, 2 edges between your pair of vertices. So those are your options that you have. Now, we skipped one of the ordered pairs in our relation, and it was the very, very first one, the ordered pair 1, 1. So using the information that we just did where we drew in all of the other arrows, we've got one last thing to put in this graph. Any guesses here what that one last ordered pair is going to look like in our graph? So this is totally being thrown to you guys. What do you think this first ordered pair is going to look like in our graph? In other words, how should I draw it in? If you've got an ordered pair and the first and the second coordinate are exactly the same thing, it is, I use the buzzword loop just because when you draw it, you start at, in our case, 1. What in the world? Come on, you can do this, Ben. You start at 1 and then you end at 1. Now, how big you make this little loop or this little arrow, totally up to you. But the key thing is you start at the same vertex where you end, so it's going to in some way, shape, or form look like either, in my case, a little loop, or if you draw it bigger, a bigger loop. And that is literally it. This is actually the thing that turns this into, from just a regular directed graph or digraph into a directed multigraph, is this little loop thing. We're allowed to have loops. Normal digraphs don't have loops. But anyway, that's not something you need to know right now. In terms of us, what happens, we can have any combination of our ordered pairs right here, and we're going to represent them by this sort of adjusted digraph. Okay? Loops are okay, single arrows are okay, double arrows are okay, and missing arrows are also okay. So that's the crash course of everything you could possibly see in terms of drawing or doing a picture of your relation, specifically finite relation built from a single set and putting it into a graph. Okay? So the other examples that I've got for us today are now going to be doing things with relations, finding properties of relations, manipulating relations, and one of the things that we're going to do is we're going to see, well, is it easier to look at the ordered pairs? Is it easier to look at the digraph? Is it easier to look at the matrix? And depending on how your brain thinks, you actually might find one of those 3 ways to be easier than the other. Totally fine. Pick the way that you find easiest. We'll go over all 3 just so you see all the ways that you have, but in terms of problems on your own, unless the directions tell you to use one way over the other, which sometimes they will, you get to pick which of the 3 ways of representing your matrix, not your matrix, your relation that you want to. So let us go one more example, and then we'll start doing things. Okay? The next example that we've got is actually the opposite of what we just did. So for this example, what it says is you've got a digraph that's supposed to represent some relation, and we want to recover the relation. Well, there's 2 things that you have to do. If you want to recover the relation, you have to know what your building set A is. And if you're going to find the actual relation is the set of all of the ordered pairs. So first thing, and I'm going to throw this one out to you guys, what do you think the building set A is here? And this is where you want to strategically go back and look at the definition of the digraph of a matrix. Where did the building set A come into play? I'll put the scratch work over here. Building set A corresponded to something. Now, when you talk about graphs, there's 2 things that happen in graphs, 2 components of graphs. There's the vertices and there's the edges. The vertices are the things that have, in this case, letters with circles around them. And the edges are the things that all look like arrows. Okay? So if we wanted to look at our building set A, where would we look in here? At the edges or at the vertices? What do you guys think? Exactly. You would look at your vertices. In this case, it would totally be the letters A through D. So A, B, C, and D. Now, if you wanted to recover the actual ordered pairs of your relation, where would you look for ordered pairs? In other words, what did ordered pairs get converted into in this graph? Or would have been converted into for the graph? Well, we already looked at vertices, so what's the only other part of the graph? And I'm not asking you to list them all out right now because there's going to be quite a few ordered pairs. But as a component or a piece of this graph, what would we be looking at? There's an official name and just a descriptor. What do you guys think? It's the only other part of the graph, are the edges. Technically the directed edges. So let me put the technical term, and that's the same thing as descriptor, little arrows. And I don't care what you say, okay? So if we want to go and find all of these ordered pairs, we'll look at all of the little arrows and we say, all right, well, do I have any ordered pairs in this relation that start with an A? What do you think? Were there any edges over here that started at A? Key thing is started at A. We're trying to find those ordered pairs first. And the answer is no. We do have some arrows that touch, or directed edges that touch A. The official word is incident to. We do have some edges that touch A, but they're all going into A, so that would mean that A would be the second position. So we have no ordered pairs that start with an A. So then we look, all right, well, do we have any ordered pairs that start with a B? So what do you think? Do we have any of our edges that start at B? Any of these arrows start at B? In other words, tails of arrows touching B. Well, I got a lot of arrows touching B. We've got this one coming in, so that one's no help. We've got this one coming in from C, so that one's no help. But we do have this one right here that's going from B to C, so that would be an arrow that starts with B. And we also have this little loop right here that would be B to B. So that takes care of all of our possible arrows that start at B. So then, just strategically moving on to C, do we have any arrows that start at C? And it looks here like we have 2 arrows leaving C, so that would mean 2 arrows start at C. We have 1 arrow that goes C to A, so that would be C comma A. And we have another arrow that goes C to B, so that would be C comma B. And that's it. There's only 2 arrows leaving C. Now lastly, we have D. And we look to see the arrows leaving D, and it looks like there's an arrow going D to A. It looks like there's an arrow going D to B. There's no arrow D to C, but there's a loop at D, so we have an arrow D to D. Now, here's how you check to make sure that you got the right number of arrows, or you got the right number of ordered pairs for your relation. You go over here and you count up the total number of arrows. So anybody get what the total number of arrows was over here? Anybody happen to get a count on total number of arrows that we originally had? So we've got 1, 2, 3, 4, 5, 6, and 7 arrows. So then you want to make sure you have the same number of ordered pairs. 1, 2, 3, 4, 5, 6, 7. Yep, we're good. So that means this guy here would be the relation where we already had the picture representation, but we didn't have the ordered pairs. So these things are what are known as a one-to-one relation. In other words, you can totally represent all the information from this relation in a picture. If you never wanted to go back to the ordered pairs, you'd never have to unless you were told you need the ordered pairs. Okay? So that's the interplay there between, it doesn't matter if you have the picture or the ordered pairs, it all matters on which format you want and or need. Okay? So now let's actually do some stuff. So what I'm going to do is I'm going to go back to the example that we looked at a second ago. Apparently the fly-ins were off by a click. So 2 things. One is something called an in degree. An in degree of some element A, which would be in your building set, is a number of elements B where B is related to A. Now this is the formal, what you would see inside of your relation. So in terms of what you're looking at here, you'd be looking for your ordered pairs, where A is in the second slot. No lies, I think in degrees are way easier to check inside your digraph. So inside of your graphical picture, the in degree is you count up the number of arrows that are coming into A, or you count up the number of arrowheads at vertex A. Okay? You can do the same thing with arrows that are leaving the vertex. So you also have something called the out degree. The out degree is almost exactly the same. You count up the number of elements, B, where A is related to B. So in this case, you've got A related to B. Notice here, A is in the first position. Personally, again, I find that this definition back in the relation, it's pretty easy to accidentally flip-flop the A's and the B's, but definitely easier to see in the digraph. The out degree is all the arrows that are leaving that vertex. Note, if you add the in degree and the out degree together, that would be the total arrows that are touching your graph, with some exceptions dealing with loops. Okay? So let's look to see how this would occur in your actual relation. So if we take the exact same example that we had previously, so this previous example right here, and I went ahead and that was supposed to come in one at a time. Oh well. So this one here is an example that we saw previously. We had 1, 1, 1, 3, 1, 4, 2, 1, 2, 4, 3, 1, 3, 2, and 4, 2. This was the original example of the digraph we had, except here I reoriented the vertices differently. I'd flip-flopped the 3 and the 4 when I drew this up previously. Okay. But same thing, just the vertices got flip-flopped. We had one loop and we had a bunch of other vertices. I also went ahead and threw in the matrix representation of this particular guy. Please note if you labeled it on the side, these would be the elements 1, 2, 3, 4, and 1, 2, 3, 4. Since you have the same building set, A in this case, our A here was the numbers 1, 2, 3, and 4. You actually get a matrix that is known as a square matrix. In other words, 4 rows and 4 columns here. This is the only time you're going to get a square matrix, is if your two building sets have the same number of elements in them. And if you have the same building set for both of the two coordinates, you'll automatically always get one of these square matrices. Okay? If you have a digraph, a picture representation of your relation, your matrix has to be square, because the digraph is only defined if you have what? If you have one building set. That's a bunch of backstory. Let's get into in degree and out degree. If we wanted to compute the in degree and out degree of this matrix, of this digraph that we have created previously, we totally could. So for example, if we put together this little chart and we list out all of our vertices, so I'll go ahead and say these guys, these are our vertices because I didn't put a label on it. So vertices. If we want the in and out degree of each vertex, let's see what it would be. So if we look at vertex, and I'm going to skip vertex 1 because it's got the loop and loops are special, so I'm going to do all the other vertices first. So let's start at vertex 2. Anybody have a guess what the in and out degree of vertex 2 is? And I'm going to ask you guys for each of these. Okay? So what do you guys think the in and out degree of vertex 2 might be? Hint, it will be an integer. 0 or bigger. Yeah, so in this particular case, you've got 2 arrows coming in, you've got 2 arrows going out. So both the in and the out degree are 2. And notice we have a grand total of 4 arrows touching 2, or officially the word's incident to 2. So that adds up just fine. Now, any guesses what the in and out degree of 3 is? So 3 is over here. So what do you guys think? What would be the in degree at 3? What would be the out degree at 3? Don't overthink it. Yep. In degree would be 1 because you only have one arrow coming in. Out degree would be 2 because you have 2 arrows leaving. And it doesn't matter that you've got these 2 double arrows going between 1 and 3. You count each of them separately because they're 2 different arrows. Okay. Then we have vertex 4. Anybody got what the in and the out degree of vertex 4 is? Don't overthink it. You calculated just like the last one. So what do you guys think? How many arrows are coming in? How many arrows are going out? So this one here, we've got 2 arrows coming in. We've got 1 arrow going out. So our in degree is 2. Our out degree is 1. And then we go back to the 1 vertex that we skipped out on. At some point, I should redo this example. So that's vertex 4, so we can just go in order. But oh well, it didn't happen today. So if we look at vertex 1, what do you guys think? What would be the in degree and the out degree of vertex 1? It's a little different than the other ones, but only because of the loop. Let's see. So the guess is 3, 2. So we've got 1, 2, 3 arrows coming in. So the in degree is definitely 3. Come on, 3. And the out degree is not 2. So any guesses on what the out degree is? The out degree is the number of arrows leaving the vertex. Yep. So it does turn out that the out degree here is 3, and that is 1 when we left to go to 4, 2 when we left to go to 3, and then that loop gets double counted. It's counted both 1 for the in degree and 1 for the out degree. So one thing that happens, and I don't know why it happens, but it has a tendency to happen when you're counting up your in and out degrees. When you get to a loop, people forget to count the loop totally, or only count one of the 2 ends of the loop. It just happens all the time. So watch out when you have a loop. What it does is it just bumps up your in and your out degree by 1. Okay? And you can have at most 1 loop on here because remember we're coming from a set, so you can't have a second copy of 1, 1. It doesn't work for the set. Okay? Now, before we move on to some other things, there's a couple things to note. 1, if you sum up across all your in degrees, and if you sum up across all your out degrees, in this particular case, we get, in the in degree, the sum would be 3 plus 2 plus 1, which is 6, plus 2 more is 8. Anybody calculate the sum of all the out degrees? What number is that sum? Also 8, yep. It turns out your sums of your in degrees and your sums of your out degrees will always be exactly the same. Anybody have a guess why those 2 sums would always have to be the same? Don't overthink it. It actually is really obvious once you get it. But before you think about it, it may not be super obvious. Actually, it's not super obvious before you think about it. So what do you guys think? Any guesses why those 2 sums, total in degree and total out degree, always have to be the same number? True of every single graph you'll ever encounter. Any guesses? Well, think about what they mean. The in degree is what? It's counting up all of the arrows coming in, so it's counting up all of your arrowheads. Your out to degree is doing what? It's counting up all the arrows that are leaving your vertex, so it's counting up all your arrow tails. So in degree counts all your arrowheads. Out degree counts all your arrow tails. Every arrow has what? One head and one tail. So that means the in degree is counting all your heads, out degree counting all your tails, and since there's only the same number of arrows in the entire graph, both of them are counting each of those arrows exactly once. Okay? So that's what's going on. So this sum right here, both of those two numbers, is the number of directed edges in your digraph. And you really shouldn't say D edges, you should say directed edges. I just ran out of space. Okay? So that's what's going on. You can also grab your in degrees and your out degrees from the matrices as well. If you add up across the rows or you add up across the columns, for example, let's pick on 3 right here. That way it's easy to see which way goes where. If we add up across the third row, we get sum of 2. That's the out degree. Why? That's because you started at 3 and you left to go somewhere else. If you sum up across the third column, you get a 1, which is the same as the in degree for vertex 3. Why is this? This is you could have started anywhere you wanted, but you ended at 3. And that's where this definition right here came into play. So notice you can get these degrees off the matrices as well, and using the original formal definition, you can pull this information off of the ordered pairs as well. But again, I think it's probably easiest to grab it off of the graph, but that's because I like the picture representation. All right, so that deals with all the basics of graphs. Let's look at one other thing that you can see inside of graphs. One of the things we're going to need when we jump into properties is length to paths, okay? So let's get a crash course on what paths are in graphs, and then we should be all set up for our properties that we'll talk about next time. So to remind ourselves, the relation is just some subset of either A cross B or A cross A. You know which one it's going to be, whether you're given 2 sets or only 1 set. Okay? Now, here's the thing about a path. So the definition of a path, and this is the formal definition inside the relation, is ordered pairs. It's so much easier in the graph, okay, representation. So you've got some relation. It's on set A. This is critical. You have to have somebody that's A cross A, so you've got the same building set in both pieces and parts. A path beginning at the vertex A or at the element A and ending at B or at the element B is a finite sequence, and it's typically labeled by some lowercase Greek letter, but you can also not name it too. Okay? So it starts at A, it ends at B, and it's got a bunch of different elements in the middle. Now, how do you tell what those sequence elements are? And please note, remember, with a sequence, you can duplicate things. Actually, with paths, you don't duplicate vertices. That would be something called a walk. But what happens here is what? You're going to have different letters. And when I say letters, I really mean elements from set A. How do you know when to put which one where? Each of these guys, so moving from A to X1, has to be an ordered pair in your relation. So you have to have A, comma, X1 in your relation. So that's the only way that you can move. Now remember what those ordered pairs also correspond to. They also correspond to an arrow in your graph. So what this path, this finite sequence, this path corresponds to in your actual graph is you start at vertex A and you follow arrows. Keep following the arrows. Don't jump and skip around where there's no arrows until you get to vertex B. Okay? You can totally do this inside of just the relation with ordered pairs as well. You can also totally do this in the matrix. In the matrix, you have to look for little ones. In the ordered pairs, you have to look for that you've got this second sequence where what happens, you've got matching first and second coordinates on the consecutive ordered pairs. But the actual path is a sequence just of the elements of your building set A. Now, that's the formal definition. Let me go ahead and throw in 3 more definitions, and then we'll jump into our example that we'll end on today. Okay? So there's also something called a cycle. A cycle simply starts and ends at the same path. So in the graph, what would happen? You do something like this, and you come back. Technically speaking, a cycle should not actually use a vertex more than once, and the first time you get back to your starting point, that would be when your cycle ends. That being said, we're not going to be super fussy about that in this class because we're coming from relations, which is different than starting from the graph. Okay. We can also define a relation called R, and then up in the exponent, there's some number. This here is a new relation that you built from your original relation R. So R is some relation on building set A. Rn is going to be the set of all ordered pairs, where in the original relation, there's some path of length n. And did we talk about length? I don't think I told you what length was, so let me go ahead and put in length here. So the length of a path is the number of ordered pairs or the number of relations in the path. Okay? Or, if you look at it in terms of the graph, it's the number of edges used. Why? Because each edge corresponds to one of those ordered pairs, one of those relationships from the relation. Okay? So n here tells you how long your path gets to be. So the one we're going to care about is we're going to care about R2. R2 is the set of all length 2 paths from your graph. That's all it is. Okay? And we're going to care about R2 because it's going to tie into one of our properties. It's going to tie into our property called transitivity, or the transitive property. So R2, the length set of all length 2 paths. So let's actually look at an example of this stuff. Oh, I had an aside here. The aside here is these different types of relations. These are relations built from the original relation R and S. I didn't bother with what the appropriate range and domain is, but here's what you do. It's the same as normal sets. So this here is R complement. This is all the ordered pairs A, B, and A cross B that are not in R. So it's regular complement. The inverse, this is when you flip-flop your ordered pairs. So if A and B are in the original R. So you just take all your ordered pairs in R and you reverse them. Union intersection is exactly the same as normal. You grab all of the ordered pairs that are in R and all the ordered pairs in S, throw them together, delete duplicates. And for intersection, take the shared ones. Okay? We're not going to focus on these too much, but you may see 1 or 2 of these in the future. If you do, you just treat these operations where R is acting like a normal set. Okay? Forgot I had that slide right there. All right. So in terms of this example, suppose you have some relatively straightforward example. It's actually simpler than some of the examples we've had in the past. We've not even touching anything and it's doing it. So we have this here, 4 vertices, 1 through 4. We've got a bunch of different edges. What is that? 6 edges, 1 loop, a couple single edges, and one of these guys edge in both directions. Okay. So what we would like to look at is we would like to find a cycle of length 1, 2, and 3 in this particular graph, or in this diagram that's a representation of some relation. So what do you guys think? If we try to find a length 2 cycle, anybody spot one? Hint, there's not always one answer. Actually, there's rarely one answer. But anybody spot a length 2 cycle in this particular graph? And while you guys are thinking and or typing, I'm going to go ahead and set up the titles for the other ones. So anybody spot a length 2 cycle? Now remember what length is. Length is the number of edges you use. cycle, you also have to start and stop at the same point. So a length 2 cycle means we're looking for where you can start at some vertex, get back to that same vertex with only 2 edges. Now, notationally, you only look at the vertices. So suppose you look at vertex 3. From vertex 3, you can only go to vertex 2. Now, if all we wrote down was 3 and 2, that would mean a path that goes from 3 and stops at 2, so that would be a length 1 path. So to get us to a cycle of length 2, we need to come back to 3. And that would be a length 2 cycle. Notice, started at 3, went to 2, came back to 3. Ah! So that's this guy. Now, anybody spot a length 3 cycle? And I'll color code it if you guys spot it. And notice, we just listed out the vertices that we went to. So anybody spot a length 3 cycle? So key things, start at some vertex, come back to the same vertex. Ooh, there's a guess. 1 to 3 to 2 to, yep, that would totally work. So we'll start at 1, go to 3, go to 2, come back to 1. So let me stop being a highlighter and we'll write that one in. So for this guy, we'll have 1, 3, 2, and back to 1. Note the length of the cycle. It has one more number in this sequence than the actual length. Watch out, that's something that messes with people's heads. Now, last question here. Anybody spot a length 1 cycle? Yep, look at vertex 4. Now, I'm having a total blank out on another Greek letter, so we'll do pi again, but I'll put a 2 there. Start at 4. Now, to actually make it a cycle, you have to have at least 1 edge. Edges are defined by their 2 endpoints. So to bump this into a cycle, this is where you'd actually say 4, 4. Let me change this color, the orange. And that tells you that you start and you stopped at 4. Okay? So that's the crash course in all the little pieces and parts dealing with the relationships, looking at it in terms of its associated digraph, looking in terms of its associated matrix. I've got one more example that I've got prepped up that'll be us finding R2, which is finding all of the length 2 paths in our associated digraph. And then next, so we'll do that at the beginning of next time. And then after that, next time, we'll focus all on the 6 different properties of the graph that we care about. And those 6 different properties, just to give you a heads up, are the reflexive property, irreflexive property, symmetric property, asymmetric property, anti-symmetric property, and transitive property. And your book has 5 out of those 6 properties in them. So if you do want to get a head start on what those properties are, they are listed out in those first 2 sections of your textbook, but I'm not assuming that you're going to read them before tomorrow. But if you want to, you totally can, okay? But that is it for today. I'll go ahead and hang out for a few minutes if you have questions, but otherwise, we are done for today.